start with a simple question about whether things are series or parallel. So let me get that rocking. Oh, good. I did remember to hide the quiz. That's always good. I almost gave you all the answers there at one time. All right. So what I want to do is warm up a little bit. Hey, if a briefcase with $2 billion is on my doorstep tonight, you guys all pass. I'll tell you what, I'll give you all A's. $2 million. That's not that much. All right. All right. So, yep. Okay. So before you get ahead of yourselves, I want you to think about, are these things in series or parallel? All right. So let's just take a quick look, and I'm going to give you a second to look at that. And so I'll tell you the answers here in a minute, or if you're waiting on me, remember, you've always got the solutions. If you don't like my pacing, do it yourself. Okay. Close, Joe, close. You know what? This semester sucks so bad. I'm tempted by that 20, Joe. I'm tempted. $53.18 would tempt me right now, man. But I'm pure. I would not give in to temptation. All right. Oh, nugget meal. Yeah. All right. Okay. So let's get to it. We're looking at these. Which ones of these are in series and parallel? And this is something we discovered last time at the end. Just because, you know, when the circuits are drawn perfectly, it's really easy to tell series and parallel. But what happens in the real world is sometimes circuits look weird, and you have to analyze them to find out if they're in series or parallel. Now, if it helps, I gave you maybe a minute to look at this. I want you to start, even though we're not talking about current flow yet, we discussed it briefly yesterday and you did some labs on it. Think about series as having one pipe for current to flow. And so you could think of current flow as water flow. And there's a whole analogy. Let's not go into that analogy right now. But just for now, think of current as a flow. So if you have a series thing, there's one pipe for current to flow. And so I think if you think of it that way, it's pretty obvious that this only has one pipe. Now, we don't actually have electrons jumping the gap there, but again, just think of this as one pipe, current is flowing. This one's series. All right. Did I get him in here? Where'd that go? Oh, there it is. Sorry there. Okay. And so, whereas these other cases, think about this, the current is going to split and it's going to flow through both of these at the same time. That is actually in parallel. Okay. Same thing here. The current's going to come out of here and it's going to split. And so it's not so much where the things are located as how many branches or how many loops that you see in the circuit. Now, a lot of you are very new to circuits, so this may make no sense to you at all. If you want to ask a question, shoot for it. And it's okay. Remember, everybody be patient. Some of you did circuits as a kid or something. This is probably easy for you. It's not easy for a lot of people. So if you have any questions, definitely speak up. I'm expecting some of you might not have a clue what I'm talking about, right? Again, if there's two branches to the circuit, that's a sign it might be in parallel. We've seen more complicated circuits, and we'll look at one next. But for this case, that's the answers. So the blue ones there are parallel. Whoops. Oh, come on. So this would be para, and this would be para. And if you want to come back for the last half of class, if this is too basic for you, you should come back for the last half because I'm going to kick your ass. All right? I will destroy you in the last half. You'll see. All right.
Do you mind if I mention something?
Yeah, go for it.
I just want to make sure that my idea.
Yeah, let's hear it. Let's go for it.
So I'm imagining that at each one of these capacitors, there's like a light bulb that is reliant on the positive and the negative. And so like, if you were to disconnect the light bulb, you know, then the connection would be disabled. If the connection is disabled and the other light bulb is still on, that means that they are in parallel. But if the light bulb goes out and you break the connection and then the other light bulb goes out, then that's in series. Series is reliant on all of them being connected.
Yeah, I think that's a decent thought process. So you could imagine you have this here, and attached to each one of these is a light bulb, right? And so you could have this wired up like this. Whoops. Right? And the idea is there was a battery in the middle on this, like one of these had a wire in the middle, right? And so he's saying, could I think of the light bulb in each of these as being sort of like the signal as to whether or not we could even do this? Put a little switch in there because you said you wanted to switch this thing on and off, right? Sorry, this is going to take just a second, but I think it's worth it for the conceptual understanding. All right. And so the idea is, oh, let's put this switch over here. So we have two different switches here, two different there, and we'll put another light bulb down in here. And so Nick was kind of saying this. Now I'm getting lazy. I'm just going to go straight to it. This was basically one of those circuits, right? And so I think what Nick was saying was in this picture here, these blue circles are electrons. All right, those are electrons. That blue on blue is not showing up. So let's make this a little darker. Those are the electrons. And now keep in mind, this battery, this is the positive terminal. This is the negative terminal. Current is going to flow this way. And so we see that this is going to be, I'll call this just I2 because that's the second branch. And there's going to be current flowing this way, which I'm going to call that current number 1. And again, current is basically related to the amount of charges moving. Now you got to be careful here. Current is going to flow out of the plus terminal of a battery and into the minus. The electrons, which have negative charges, are actually going to flow the opposite way. So electron flow is going to be the opposite way here. Negative charges flowing clockwise would be the same as current flowing counterclockwise. All right. So there's a voltage on this battery here. Usually we say the voltage of the battery is script E. So you're going to see me use an E for the battery all the time. And what Nick was saying here is if I drop this like this and drop this like this, right, what we see, ooh, I need a third switch in here, all right? So let me open this here. That way I could turn them both on at the same time, you know what I'm saying? And let's do this. And then let's discharge these and start over, sorry. It's the other capacitor. Sheesh. All right, let's get both of these switches up. Give me a second. Sorry. That's actually the last half of class right there. All right, so there we go. All right, so in this case, right now, notice the battery, this switch that I'm trying to wiggle. Hopefully you can see this. I just had this paranoid fear that I forgot to screen share for all of this. Anyways, yeah, so I'm going to close these two switches, and we don't see any current flow because this switch is still open. So when I close this, you can see the current flowing to the two capacitors at the same time. And there you can see they're both running at the same time. And notice when those light bulbs go out, we don't see them. We don't see the charges moving anymore, which I think is what you were saying, right, Nick?
Yeah.
Yeah. And so if I could go here and take this one step further, we'll open these up again. And we'll just discharge all of these. And now if I keep this switch up top open at the same time and close it, notice current can flow through the left one, but it can't flow through the right one. So clearly they're not in series because there's a way to get one of the light bulbs lighting up when the other one is not. And I think that might be the ending reasoning that Nick was talking about. Correct, Nick?
Yes, exactly.
And I agree with you. So that looks great. There's another way to do it too, and check this out. And let me clean this up a little bit, okay? So with this circuit, in this case, here's another way. We could leave them all charged up, and that's fine. You can look at the nodes. This is a big pink. So this big pink dot, that's just a reference spot, right? That's just a location I want to refer to. So I could say the pink spot. And in circuits, I would say that's not a pink spot, that's a pink node. All right. And then down here, I'm going to make an orange node. Here's another way to tell these are in parallel. Aren't they both connected? Let's say this green capacitor over here and this blue capacitor over here, they are both connected with one side. Oh, jeez. One side of this is connected to the pink node, right? And the other side is connected to the orange. Well, for the green one, we can see that one side is connected to the pink and the other side is connected to the orange because both capacitors are connected to the same two nodes parallel. That's another way to see it. Here's a final way to see it. You could also do this trick. Split this junction, move this way over here, split this junction, and move this way over here. Then I could move all this crap way over there and just rewire it. And it's the same thing. Whereas now you could clearly see these two capacitors are in parallel. And so you could do it that way. That's the stretch technique, right? And so there's another way to see it. If you see that you could, and now this again, you might be saying, wait, didn't you do something illegal? Nope. This is still that pink node. And this is still, I think I used orange. That's still that same orange node. And notice all three of them are still connected that way. So this is an equivalent way. And now in the circuit that we showed in the book, this light bulb wasn't here. So we could remove this and remove this just to make it look more like the picture in the book. And so there we go. I'm going to pause and see if there's any questions about that. And there's one in the chat.
Yeah, could I ask a quick question?
Yeah, go for it.
So does it matter which side? So like in that example, the light bulb on the right was on the positive plate. It was like above the positive plate. So like current would flow directly to the bulb. But then on the other one, the light bulb was on the negative terminal. So like, how did, like, does that, because that didn't affect obviously like.
Doesn't matter.
Yeah.
Let me show you why. So this is a little bit tricky here. I'm going to go to a different simulation and try and show you. Whoops. Let me clear my annotation so we're on a different screen. That's a great question. I think I know what you're talking about here. So in this case, now watch when I turn this on very briefly. I think you're going to see an arrow here and an arrow here. Okay. Watch when I turn this on. Just a second. 1, 2, 3. Here we go. And I don't know if you saw those arrows.
Yeah.
And then if I, and then watch it again. So that's supposed to indicate that temporary current flow. And the idea is this. And let me see here. Let me get my annotation out. Okay. So in just a second, I'm going to make this positive 1.5 volts. I think you expect that this will then be the plus terminal. And that'll be the positive side of the capacitor. And then down here, this will end up being the negative side. So was that Travis? Or no, who was that was asking the question?
Yeah, that was me.
Okay, so Travis, initially these plates aren't positive and negative. What type of charges are going to move in here? Electrons or protons?
Electrons.
Electrons. Which way are they going to move? From which plate to what plate?
From the negative plate to the positive plate.
They're going to leave this plate and make it positive. Does that make sense?
Okay. Yeah.
So you're going to have a bunch of electrons that are like, dude, that battery's making me move. I like that groove. So it's going to come around here, and these are going to be the electrons moving. Now, this is weird. In physics, we actually call this the current flow. If you don't like it, blame Benjamin Franklin. He's the one that did this to you, not me. Okay. So current is going to flow this way, which means electrons, which are negative charges, Is that good on that part, Travis?
Yes. Yeah, I get that.
All right.
Yeah.
And so now let me ask you, you asked a question about a light bulb. Let's say I put a light bulb down here, and that light bulb is effectively like just a little resistor, and it gets hot and emits light, okay? That we're going to go incandescent for right now. Now, in this case, if you have charges leaving here, aren't they eventually going to have to go through here as well?
Yes.
And
Okay.
so it doesn't matter which plate you hook it to, because at the same instant in time, all the electrons in the wire start moving this way. So all of them move. And believe it or not, it actually takes about an hour for a single electron to go all the way through the wiring in your car battery, to go from one terminal of your car battery to the other. So each individual electron does not move that fast. Well, actually, it moves very fast, but it's bumping around randomly forwards and backwards, on average, drifting slowly. More on that next chapter. That said, go ahead.
And so obviously, like you were talking about, like the electrons aren't, it's obviously not traveling across the space.
Right. And so when they get
polarized,
here,
like, because the plates are polarized.
Yeah. And so what do you get? That is correct. The plates become polarized. And do you agree you create an electric field?
Yeah.
Between the plates?
Yeah, just like we were working on last time.
Yeah, exactly. And it turns out at the very end of this class, the last week of class, I will tell you that this electric field that changes is equivalent to a current called the displacement current. This was one of the craziest things in physics back in the day. They couldn't figure this out. It turns out the changing electric field is equivalent to a current called the displacement current. And that was one of Maxwell's big contributions. And that's why they're called Maxwell's equations, because he figured out that capacitors aren't crazy. You have to think of the electric field inside when it changes as being equivalent to a current. And when you do that, it turns out you could think of this current as flowing, even though no charges go between them. Is that good enough for now?
Yeah, that's good enough. Just to know, yeah, so that because you're still having that flow of electrons, even though they're, because of the polarization, like your current at the bottom is the same, like the current's the same through
the entire wire,
the whole circuit, because of
exactly. And if you view this changing electric field as a current, which was not obvious at all, this was very crazy, right? If you view that, this is now a single pipe and all the flow, right? So the current's flowing this way, flowing this way, flowing this way. The electrons are going the opposite way. Is that good enough on that?
Yep, that's perfect. Thank you.
Yeah, and so I guess we could stop class now and be done for the semester. Yes. That was the last chapter.
Nice.
All right, good luck on the quizzes, everybody.
Did it.
I'll get the McNugget.
Yeah, you got it.
All right. Okay, so next, all right, let's get back into the problems. Let's see here. So that was good. That was a good warm-up, and I'm telling you, I wish I could do this stuff separate, but you kind of have to just kind of keep fighting your way through it. So you'll probably understand capacitors a lot better after we do resistors. I'm not kidding. That said, so this capacitor chapter is probably going to feel a little tough, and then it should get easier. The math isn't that bad. Let's take a look at this sucker down here. All right. So I want to look now at, let's do this one. Okay. And I notice I should mention here, when you see this, that's what I'm expecting for you. I expect you to do the setup and try and work this thing out. I'll explain more about that in a minute. Actually, why don't we, let's do 25.11. Okay, I'm going to draw this on the board, and you guys can get ready for it too, okay? I'll line up the board later. Remember, you have the solutions too. So if I'm not going at the pace you like, try to use the solutions. Or if you're having trouble following my pictures and stuff, you know what I mean? Follow those solutions. Almost there. This is starting to look a lot like quiz questions now, where I don't give you numbers and I give you a bunch of letters. Okay. And some of them might have numbers too, but okay, I think I got it. Oh. Whoops, there we go. All right, so we got this question here, and maybe I'll go back just a little bit here. All right, and so we are told these pieces of information. So why is this thing? There we go, get that off of there. All right, in this case, we were not told any information about the battery. Do you agree? All right. There's going to be questions like this in the real world. Why would we ever, you might say, why would you ever ask this kind of question? Here's the idea. A lot of times in the real world, you're trying to figure out what battery you should use. So what you do is you say, well, if this is what I have to work with, I'm going to pretend I know what this battery is, do a bunch of math algebraically, and then I could plug in different numbers for the battery and see how this situation would respond. So that's the idea is, let's say you wanted to design a new circuit, we might need to figure out what battery that circuit should use. The general strategy for this is as follows. Pretend you know what the battery is and stick in a known value, but then at the end we'll say, wait, this is unknown. So pretend this is known, work out all the math, and then at the end of the problem, we can discover, hey, well, if this is what's known, let's say, oh, well, that relates to E. I don't know if that strategy made sense, but let's try and work this out and see what happens. Okay, so we need to figure out this circuit. Is it in series or parallel or a mix? What do you think?
Mix.
Mix, I agree. So where should we start? Which two capacitors should we start with?
C2 and C3.
C2, C3. And these two are in, and since Nick, you've been answering, I'll keep hammering away. Nick, what do you think? Series or parallel?
Series.
How can you tell? Same pipe, I guess, or something like that, right? Okay, so in this case, C2 is 2C, C3 is C3, and then during test day, you're fortunate that you will have this crazy looking chart here. Whoops. So I go, hey, I'm making a series combo. I'm going to use the series shortcut. Don't forget about this one. You'll see this in the homework if you actually do it. So don't forget about this shortcut, though. Saves a lot of time. I'm going to not use the shortcut just to make sure I could show you one mistake students usually make. Okay, so 1 over C23 should equal 1 over C2 plus 1 over C3. Well, that's equal to 1 over 2C plus 1 over 3C, which that's equal to, let's see, 3 over 6C plus 2 over 6C. You could punch it in your calculator if you wanted, but notice this is 5 over 6C. Is that the capacitance?
No.
No way. C's in the basement. You got to remember this is 1 over C equals that. So C23 is equal to 1 over 5 over 6C, which is equal to 6C over 5. Know what I'm saying? Watch out for that. A lot of times people just forget to, wouldn't that suck to lose points because you forget to unreciprocal it or whatever you want to call it? Now, here's a check. I like having checks on my answers. If you're listening, check this out. Well, I know this one's 2. And let's see. Oh, do I want to do that one here? Well, it should always be smaller. If you have 2 in series, 2 capacitors in series, the equivalent capacitance should always be smaller than the smallest. And it is, and that's a check on it. So C should be on top. This is smaller than the smallest, looking good. All right. So I think we're all good to go. So I'm going to do this way. I know you've got the workbook to follow along. So I need to erase 6C over 5. Got it. And these two are both C. I don't know this voltage, E, but I'm going to pretend I know it because it hasn't come up yet, right? So don't give up if something's unknown. All right. And so this was, to be clear, this one over here was number 1. This one was number 4. And this is 2, 3. The combination of 2 and 3. So now somebody other than Nick, which capacitors should I combine to keep this rolling?
2, 3, and 4.
2, 3, and 4. So now, and are those series or parallel?
They're in parallel.
So should I do the 1 over adding or just add them?
Just add them.
Yep. And so what am I going to get? Because this was C. I don't know if you remember. What are we going to get here?
11C over 5.
I dig it, man. That sounded like Eston, right?
Yes, sir.
Right on, man. And make sure I don't screw up. Is that what you said? I think that's what you said, right?
I think that's what I said. Yeah.
All right. And then, all right, somebody other than Eston or Nick, what do we got to do now?
Back to series again.
Back to series because it's 1 pipe. And so here we go. That's going to be, all right. So now I'm going to use the shortcut. So C times 11/5 C divided by, what is that, 16/5? So it's the 2 times each other over the sum, right? So C plus 11 will be a 5. All right, so I don't want to screw this up. The C's cancel, the 5's cancel, and we get, what is that, 11/16 C. Check. Does it have the C in the right place? It's in the numerator. What did I tell you earlier? This is a series combo. It should be smaller than the smallest one. Well, this is 16/16. It's a little smaller than that. You could tell this, by the way. If they were exactly the same size, the capacitance gets cut in half. All right, so in series, capacitor, it's a little bit weird. It's like the exact opposite of resistors, okay? All right, so there we go. So I'll explain that logic in just a minute after this with a simulation, okay? So after all this, the point being was, oh crap, I just erased it. What was it, 11/16?
It was 11/6.
Thanks. Now that we get it down to just 1 capacitor left, now, no, they have opposite rules. Jay, it's a mix. Let's worry about resistors some other chapter, 2 chapters from now, okay? More on that after class or something, all right? So yeah, now take a look. At this point, when I have 1 battery and 1 capacitor, I know everything. So I know that this voltage is going to equal E. And I can get this charge. Let me write that in a different color here. The charge on this puppy should equal, it's EC, right? It's so easy. Q equals V. So bad. Okay. It's so easy. And it's covered in glare. All right, there we go. All right, so the idea is I got this from this equation. Q equals delta V C. And I know that this battery has voltage E. Well, in this case, there's only one capacitor, so all of that voltage is absorbed over this capacitor, so I know that voltage is E. That's conservation of energy. Next, I get the charge using this. And we may also need, flipping this around, delta V should be, what is that, Q over C? So these are our two rules we could use back and forth. All right. Okay. All right. So next, what do I bring back to this circuit? The charge or the voltage? Which thing comes back? Somebody else.
Charge.
Charge. Let's see. And that was because in series, right? Great. So then which capacitor do we really care about in the end? What is the, okay, because remember, let's keep our eye on the prize. We did all this work. What are we trying to find? The voltage of the battery, right? I think. I guess I should have read the question. Where was this question?
2511.
Okay. Yeah. And so this was part A, wasn't it? Sorry, that was part A. And then I jumped into part B. Part B says determine the potential difference across the battery. So part B, so this was part A, great. Next, part B is figure out E. How am I going to figure out the voltage of the battery? What is the known that I haven't used yet? Q3. So the idea is we work our way backwards, ignoring everything but the one thing that we know about. We're going to try to get to Q3. Why? Because if I could keep bringing this shit backwards, eventually I'll have an equation that's going to have some E in it and Q in it, and I can solve for E then. Got it? That's the design strategy that we're doing. All right, so that said, somebody said bring back the charge here. So this is 11/16 EC. So I can get the voltage from this. The voltage is Q over C. Geez, I don't want to screw that up. Is that going to be 5/16? I'm running out of room here. So the voltage is Q divided by C. So I think the 11s will cancel, the 5 will come up top, and we'll get 5/11 E. Is that what you got? So again, I just used this, plugged in that. I've got to do it by hand because I don't want to screw it up. It is smaller than the battery's voltage, which is a good sign. We don't want to suddenly have this voltage be bigger than the battery. All right. I got to do it by hand. Sorry, I just don't want to screw up. 11/16 EC over 11/5 C. The C's drop, the 11s drop, times it by 5 on the top and the bottom. Yeah, I got, oh, wait a minute. It should be 5/16, shouldn't it? Is that right? I screwed up. All right, I'm glad I checked that. All right, moral of the story, don't trust your brain. But you figured that out by now. All right. Okay, now, do I care about this one? No. That doesn't get us anything. We already know what we need to know. Would that be useful as a check? Sure. But do you have an infinite amount of time? No. So keep your eye on the prize. We're going for C3. So now I'll come up here. This was C24. So now what do I bring back with me? Somebody else, somebody new. Here I did a parallel combination to make this one. So what do these parallel capacitors share with the equivalent?
Same amount of voltage.
Voltage. And then since I don't care about 4, I'm going to say this one has 5/16. E. All right, and from that, couldn't I get the charge using this stupid equation? I bet I could. So, So 5/16 E and this is one of those chapters where I actually kind of like doing the fractions instead of decimals. You'll notice I work these out that way. And then at the very end, sometimes I'll do decimals. But a lot of times by doing the fractions, usually something's canceling out, right? So if you get a term where nothing cancels out, sometimes you think, oh, did I screw up? So in this case, actually keeping the fractions, there's a reason. I think it reduces mistakes. Oh, we got a 6/16. I guess we could write that out. What is that? 3/8. Hopefully I didn't. 3/8 EC. And so now this one, C23 was comprised of a series combination. So we should bring back the charge. And so now, wait a minute, that's all we needed. Aha, Q3, which was equal to Q, was equal to 3/8 EC. I could see that E is equal to 8Q over 3C, and I'm done. And so now I know if somebody gives me this stupid apparatus and I need to figure out what voltage to apply, I'd say, well, if I want to have this much charge on there, I need this much battery. And that's a slightly useful thing. Okay. What do you think? I don't know. Questions on that?
Are we still going to do part C of that?
Oh, what was part C?
Determine the energy stored by C4.
Ah, okay. And so now, okay, this is a good question. Let me see here. Let me do one more thing so I have some room to work. Thank you for reminding me of that. Do you agree that these two have the same voltage because they're in parallel with each other? Thank you for reminding me. Now, the reason I'm saying that is I need to erase the bottom of the board so I have some room to work. That's all. Okay. And again, these two made this parallel, so I brought back the voltage. I could do that to both of them. So that's great. Thanks for reminding me to do that last part. So the question was, how much energy is on number 4, right? Was that it? Yeah. Yeah. Okay. So in this case, was that Travis? If so, what's the formula here? If not, whoever that was, tell me the formula. What's the formula for a capacitor energy? The general formula.
1/2 Q delta V.
Delta V.
And yep. And so let's call this 4 and this one 4. So now, right, I'd be, if I want the energy on number 4, I need the charge on number 4 and the voltage on number 4. Now, we could do this another way, but I want to show you this style. Wait, don't we know something about Q4? Don't we have an equation for it? Q4 would equal delta V4 C4, right? So rather than try and figure out the chart, let's just do this and shove that in there. So what we do is we could now say, isn't that going to be 1/2 V squared C? Right? And so now we already know this. We know this. We're done, basically. Let's plug it in. It would equal 1/2 times V4 was, and C4 was C. This I would shove in a calculator, but look at the units. We're going to get E squared C. And some number here that you could punch. This is one I would just punch in the calculator. Just and maybe I'll do that really quick. But you've got it in your answers, so might as well finish it. We're so close. 0.5 times 25 divided by 256, 0.04883. Oh, wait a minute. E is an unknown, isn't it?
Yes.
Shnikes. So, fortunately, we did this part. Do you agree? That was a bad move on my part. I forgot E was not given. So, remember, this is something good to see. Don't forget to always read the question again and see, okay, did I answer in terms of the givens? And in this case, E was not given. So, all right. So, oh, man. All right, let's figure that out. So that's got to be, oh man. So times 864 over 9. So 0.347. Now look carefully. That's going to be Q squared over C, because you have a C here. You get Q squared over C squared times a C. You should get Q squared over C. So maybe, hopefully that's the number I wrote up. All right. And hopefully I didn't punch in the numbers wrong, but so far so good. What do you think? And so this is the way I like to phrase questions, without numbers. Why? Because it's so easy. But I know that seems crazy, but after a while, you'll kind of get used to doing this. But this won't be easy for the first one to maybe the third problem. It starts to get a little easier. By the time you do 5 of them, you're like, okay, I got this locked. And this is the kind of tricks that I do where I'm like, oh, you do all the math and then you got to work all the way back and then you get to use your last known. So I've showed you my trick on this type of question. I don't know if there's much else to say about this type of problem. It's not easy identifying if two things are in series or parallel, but now you're starting to see this, hopefully. Whenever two things have a single pipe, think of them as being in series. And then whenever you have the two branches, you think of them as being in parallel. It's not really going to be locked in until we do resistors. All right. So you got to do your best on this one. Just try and identify them. All right. Let's take a look at something here. So I tried to give you problems in the workbook that force you to deal with weird angles and stretching and thinking, so that on the quiz, when everything's rectangular, it won't be that bad. I hope. But, you know, like here, a lot of people, sometimes they think 1 and 4 are in parallel with this thing, but they're not. Because you see, if you do things in order, grab the complicated one here, then you're like, oh, shoot, this one's stretched all the way around. So watch out for that. Yeah, watch out for that. So here's another variation, right? So definitely try setting this one. It looks easy, right? I don't know. Maybe it's not that hard to finish. So you should at least do the setup on that, but probably do it all the way through. That gives you, right? It's a variation on what we just did. It's a little different, okay? Notice it gives you energy. I skipped over this one. I'm going to let you do this one at home, but maybe don't try to overthink it. Use this problem to learn from it. And so take your guess, read the solution, write down what it actually was if you were wrong, okay? So with 25.10, do not spend all day on it. Think, maybe even talk to a friend with that one and have a friend to discuss and say what you think it should be without looking at the solutions, okay? And then go look at it and say, oh, and maybe you'll learn something. So that's what 25.10 is about. I'll skip that one. Great problem for dealing with the angles. Just more practice. More practice. And this one's pretty good. This one I kind of like for this reason. The first thing you're supposed to do is sketch the picture so we could see if you can understand not only the pictures, but also the words. And that will be quizzed. Maybe, I don't know if it's the capacitor quiz or the resistor quiz, but I definitely, maybe it was a lab. I don't know, but sometime that's going to show up. So definitely do this one. I can't remember anymore. My brain is just fried. Okay, so I'll leave you there on that one. So this is another one of those kind of, I give you one of the energies and deal with it. All right, this shows you a pretty good reason why you would do that. In the real world, most capacitors have a rating beyond which you should not go or you cause them to explode, right? If you're using a dielectric capacitor, and you don't want things to explode. So there's a reason you might do this problem where you're like, okay, if I have this capacitor in here, what is the largest voltage I could use? Make sure whatever's coming in from my signal is not that big or I'm in trouble. So there's a reason you might actually do this strange procedure we are talking about. All right. Questions about that? All right. Let's keep rolling. Oh, yeah. Oh, yeah. Okay. So we're about ready. Oh, most students hate this next part. Good. All right. Before we go into that, I want to show you something else. And let me see if this has got it. Oh, come on, come on. Control Alt Shift H. Okay. Now, in this case, here I have two capacitors. All right. And what I'm talking about right now, oh, sorry, I have one capacitor, but I'm going to put 2 and 3, etc. Okay. So I'm going to change them around in a minute. So in just a second, I'm going to add capacitors, and I'm trying to motivate why the rules are the way they are. Maybe you're like, I'm tired of these stupid rules. Why are they that way? Well, I'll give you just a second here and I'll show you why. Imagine we know C1 is a parallel plate capacitor. I know the capacitance is epsilon naught A over D, right? And I'll just put area 1 and distance 1 here, where distance 1 is this, right? The distance between the plates. Now that marker is really fat. I'm going to try and slim it down just a little. All right, so what if I add another capacitor? Now this is probably going to screw up my drawings, but we'll fix it. So let me fix that. So up here, right? Think about this. It's almost like when you add two equal capacitors, and let's get the total capacitance. Notice the total capacitance cuts exactly in half. It was 1 e to the negative 13, and now it's 0.5 e negative 13 farads. Why is that? I like to think about it like this. When you put them in series, it's almost like you have twice the distance. You see that? And so twice the distance comes in the denominator. That cuts it in half. Think about this. If you put these really close together, instead of having this plate, you'd basically have this, right? You could have one piece of metal in between. This piece of metal, this piece of metal right here corresponds to these two plates shoved right next to each other with no wire in between. Okay, and the idea is you can see this. The spacing has doubled. And so that's why, effectively, when you put capacitors in series, the capacitance actually decreases. It's like you're putting the plates farther apart. All right, any questions about that? Okay. And I'm sorry if I'm cutting you off too soon. You could throw it in the chat or whatever. I just have no idea, so I'm just doing my best here. Let's look at them in parallel now. You can almost imagine taking this piece of wire and making it really short, and this piece of wire down here, whoops, let's say this one. Oh no, I need a different color. And this wire down here and making it really short. And if you did that, what would these look like? It would look like this plate right next to this plate, and it would have twice the area, right? So when capacitors are put in parallel, you're effectively doubling the area while the distance is the same. And notice we double the capacitance. And that's because the capacitance, the area appears on top. And I hope that at least gives you a feeling for why this works out. If you double the area, we should get twice the capacitance. So that's why capacitors in parallel add them up, right? You just add up the areas in the numerator. And you could see the 1 over rule is going to come in series where these distances add up. You have to 1 over it. I don't know. That's not a technical term, but maybe that makes some sense. So far, so good on that. That's just to give you a feeling for why these rules are the way they are. Ryan, did you have a question or no?
No, makes sense.
Okay, cool. Sorry. I think we should move on to the dielectrics now, unless I don't know. How are you guys feeling? Are you feeling like you kind of understand the stuff that I just did up here with these circuits? Just kind of give me a yes, no, a wavy hand or a thumbs up or a thumbs down if you want.
Yeah, I completely messed up the working backwards part, but I'm sure I can figure it out.
Okay.
Yeah, I feel similar. I think working my way down, I got that pretty on lockdown, but working my way up, I think I just need to do,
a couple more
problems and
a couple more. Okay.
But, just
yeah. So then in that case, I figure we might as well there's a lot of those places to make mistakes. Hopefully what you'll find is I don't remember what I put in, but I think a lot of times what I did is I wrote the capacitors in terms of numbers times C. And then on the Canvas quiz, I think what you're supposed to do is type in the number that should be in front of C for the equivalent, or the number, like in this problem, I already lost what it was. Was it 5/16 or so? What was the equivalent capacitance? 11/16 or something?
I think it was 11/16.
Yeah. So like if we had done this problem on the Canvas quiz, what you probably would have to type in is 11 divided by 16. And so you would type in 0.6875 or whatever I said there. Right. And you wouldn't type in the letter C. So for the equivalent capacitance type question. So you could tell you're probably going to do all right with that. Most of you. And then there'll be another question probably where you got to work somewhere backwards or something. And then there'll be the stuff like what we're about to do soon. Let's foreshadow that, then take our break. Oh, let's check the chat here. Okay. Yeah. Okay, cool. And then I guess going back to Jay's comment, resistors don't have the same rules. Well, let me rephrase. Equivalent resistance doesn't have the same rules. It's flipped. And we'll see why. It basically comes from what I was just saying a minute ago. For capacitors, you get area on the top and distance on the bottom. For resistors, it actually flips. The longer a wire is, the more resistance it has. So for resistors in series, you add them up. And then for resistors in parallel, that's like adding extra area to the pipe. It makes it easier for water to flow. So if you add extra branches, add extra resistors, it's actually easier for current to flow if you add them in parallel, because you're effectively increasing the area for fluid flow through the pipe. So that's what gets flipped. Now, what doesn't get flipped is the basic fundamental physics that voltage of things in parallel is always the same and current of things in series is always the same. So for capacitors, we've been saying that in series, they have the same charge. Well, charge and current are very related. They're basically the same thing with the derivative. Okay, so if you have the same current in series, you're going to have the same charge in series. And if you have the same voltage in parallel, that's still true. So Jay, now I finally had a chance to answer that question. Are you good enough for now on that?
Yeah, that makes sense.
Yeah. So some of the rules flip and some of them don't. Yay. All right. Just typical physics. All right. Let's go back to a screen share real quick. And let me see. We're going to finish today with these dielectric in-outs and then turning the switches on and off kind of stuff. So dielectric. A dielectric is an insulator. All right. So, for example, earlier this semester, remember when we did the rub the balloon on the head and it sticks to the wall, or Franklin's bell and those types of things? We talked about polarization and insulators. Yeah. So you could think of this dielectric here. Let me just show you this. I'm going to charge this up, and this yellow cube that I'm trying to wiggle right now, hopefully you see it wiggling by now. When I stick that in there, watch these charges carefully. So where's my, go ahead.
Isn't air a dielectric too?
Yep.
Then?
Air is a dielectric, and air can be polarized. So is sulfur hexafluoride. So is glass. Now, here's the thing, Nick. No matter what you think is an insulator, if you apply enough voltage, it's a conductor, right? Lightning happens. So air can conduct electricity. However, it doesn't easily conduct electricity, so we call it an insulator. Plastic usually doesn't conduct electricity very well. About 10, 15 years ago, they made conducting plastics, and that got a Nobel Prize down at UCSB, right? So maybe that was 20. Maybe I'm old, whatever it is. Yeah, but so semiconductors, right? Sometimes they're good conductors, sometimes they're not. It depends on the temperature or the amount of doping. So there's all kinds. It's sort of like manic depression. Everybody has, they're somewhere on the scale, right? And everybody has some level of mania and some level of depression at some point. Otherwise, you wouldn't be in this class, right? You must have been crazy to take it. So at some point, we're all on the spectrum. At some point, every insulator is on the spectrum as well, right? So meaning every insulator could conduct, right? If you just apply enough voltage. So yeah. All right. That said, what was I going to do with this? Oh yeah. Nick, did I address your question or not? That's a long way to address it.
Yeah, you're good.
Yeah, right. So in this case, this is an insulator, but obviously if you had a 10 billion volt battery, it would suddenly become a conductor. All right. All right. So watch these charges as I bring it in. Now, what do you think should happen? Think to yourself, what's going to happen to them? It's a piece of plastic, basically, or something. As I bring it in, look at those charges moving around. I know this sounds a little bit crazy, but you could think of this when this thing gets polarized, it's almost like it's decreasing the plate separation. And you could read a book about this if you want. But the idea is, notice that charge actually goes up. And when I pull this back out, I can't get as much charge on those plates. So when the dielectric is inside, it's actually easier to get the charge separation between the two main plates, right? The dielectric's polarization helps us basically decrease the plate spacing effectively. All right, it's not really doing that, but it's kind of doing that, all right, in the sense of you can get pluses and minuses a little bit closer together. Now, if I could, let me turn this off. All right, and I want to show the capacitance. Now, right now, and I'm going to disconnect the battery. If I bring this dielectric in, will the capacitance change? Yes or no? Think to yourself.
It should go up.
Exactly. And I was trying to point out the capacitance is independent of the battery. Thank you. Good job. Right. And so we see, whoops, let's bring this in here. The idea now is if I bring this all the way in, I get 0.44 up here. So I'm watching this number right here. Okay. When I bring this thing out, the capacitance goes down. The capacitance is a property of the geometry. Bringing in the dielectric is effectively changing the geometry. That's how I like to think about it. So far, so good on that.
I do have a question. You said
go
it
for it.
changes the geometry, but like,
effectively
in what
changes
aspect?
the geometry. It doesn't really change the geometry. It's these charges coming in here. are able to be polarized and effectively reduce the separation gap. The separation gap does not actually decrease, but when that thing is able to polarize, it effectively decreases the separation. So it's not
Okay,
really.
That's what I was asking. Like, which aspect did it change? Was it the separation or was it the area? Like,
Yeah, exactly. So I think of it as effectively reducing, because think about this. If this thing gets polarized, right, you're going to get some minuses here, some minuses here, some minuses here, and then you're going to get some pluses here, some pluses here, and some pluses here. Now, I know this may seem a little crude, but these two kind of overlap. These two kind of overlap. And what you've done is you've been basically brought a plus charge closer to the negative plate and a minus charge closer to the positive plate. That allows it to attract more charge onto that plate for the same separation. So you could kind of think about it as reducing the separation to just this separation instead of that big one. Does that kind of make sense?
Yeah, that's good.
Isn't that crazy though? Crazy. All right. So now a lot of dielectrics typically range between 1 and about 5, as you can see over here. So okay, that's cool. What else did I want to say about this? That's one thing a dielectric does. Now, this is where things get spicy. Let's connect the battery. Okay, I have this charged. Now, we saw what happens when I bring this in while the battery is connected. The capacitance is going to go up. I still have the same voltage. So let's write down an equation and let it govern our thinking. We know that Q equals delta V C. If the battery connected, sorry, I got to write this out. If that connected, do you agree that delta V is going to be fixed? I can't change the voltage while the battery is in there. The battery is a device that forces everything else to fix to that voltage, okay? So that's something, I guess, that's maybe counterintuitive. C is going to go up. We saw the charge is going to go up. Duh, piece of cake. All right, now let's play disconnect the battery. It's a very fun game. Kids play it all the time. Disconnect the battery, don't you know? All right, so now predict what should happen. When I bring this in here, what should happen? Think to yourself or chat with a neighbor or just, play a quick game of online poker. One of those three. All right. I'm going to write my equation just so I have it to play with. If the battery is disconnected, we know the capacitance is going to go up. Which of these other two is held fixed? Charge or voltage?
Got to be the charge, right?
Yeah, why? I guess.
I know where to go.
Yeah, it's got nowhere to go. There's no wires. There's no way. Charge is conserved. It doesn't just magically disappear. Now, so what is that going to do? Well, which thing should change then? We know that the capacitance changes, but this doesn't change. So do you agree that the voltage must change?
Yeah, the voltage has to go down.
Yeah, and so I'm going to solve for that in this equation. Delta V is equal to, what was it? Q over C. And so now, if this stays constant, and the capacitance goes up, the voltage must go down. Let's get out our voltmeter and check it. So this is counterintuitive to people. All right. Let me connect the battery again. There we go. So now we're at 1.5 volts. I didn't slide the slider all the way up. Sorry about that. So just getting this dialed in. So now it's at 1.5. I'm going to disconnect the battery. When I slide this in, watch what happens to the voltage on the meter. So again, we're looking at this number right here. Look at that voltage as I bring this in. I wrote all over it. Jeez. It goes down, right? And as I bring this in more, it just keeps going down. And notice the amount of charges on the capacitor is not changing, right? We're basically having the same amount of charge. What's going to happen to the energy? Rather than guess, what could you do?
You could do an equation, but doesn't
Right?
it gains energy, right?
Well, let's find out. U is equal to 1/2 Q C delta V C, right? Tell me, and this is a cool trick, everybody. We want to analyze this. Write the equation in terms of that and something that's not changing. So in this problem, should I write this energy in terms of Q, V, Q and V? Which one? Which thing is not changing in this scenario? I think it's Q, right? So take a look. Let's rewrite that using this equation. Isn't that Q squared on the capacitor over 2C? C is going to go up. Okay, double check that I did that right. All I did was I tried to take this equation right here, shove it in for voltage. I get Q squared on top, C on bottom. If C goes up, U goes down. Let me see if that's true. All right, so let's bring this back out. Stored energy. All right, so let me do this. All right, so I'm going to start bringing this in. It says I have 1 joule, or 1 times 10 to the minus 13. And as I bring this in, I actually have less energy. Where did that energy go?
I thought it would be more since you're using energy to push it into.
Oh, but that's not true, is it? The energy went down, so that can't be true. Agreed?
Yeah, agreed. But that's what I thought it would be.
Yeah, but so now let's try and figure out. You said I had to push it in there. That's clearly not true, is it?
So that means it's pulling it in.
It gets sucked in just like a magnet. Isn't that crazy? What? Notice the energy goes into separating these frickin' dipoles. What? Isn't that fun? I'm telling you guys, this class gets more and more fun with time, even though it sucks that first 4 weeks, okay? So now Alexa says, what would cause the disconnected capacitor to go away? In reality, there is still a circuit here, Alexis. It's just a really shitty one. The circuit is the air molecules surrounding it can actually connect it like a wire, because there are charged molecules in the air all around us. Particularly water vapor is pretty good at getting, hydrogen can actually get polarized, and it can effectively pick up a negative from here, carry it around, and eventually a different hydrogen might land on here and drop off a negative. So the air is actually a really big resistor that's slowly leaking the charge from one side to the other. More on that in 2 chapters. Is that good for now?
In 2 chapters, are we going to talk about that?
We're going to talk about RC transits. Yeah, so right now we have talked about capacitors only. In the next chapter, we're going to talk about resistors. The chapter after that, we're going to talk about lots of resistors and capacitors. Then we're going to talk about magnetism. Then we're going to talk about induced voltage. Then we're going to talk about inductors, and then we're going to talk about RLNC and the wall socket. And then we'll talk about radiation, and we're done. So we really have covered the whole semester. Now I can quit. Or take a break. I don't know. Yeah, jeez, I'm getting, by the end of the day, my Zoom just goes a little crazy because I lose it in here talking in these headsets all day. Did we, let's try and focus on something here before we take our break and make sure you got it. Number one, I think I have this written down. Let me see if I got this here. Just give me a second. I love that. Is there another more annoying method? Oh gosh. Yeah, there would be with me. Oh my gosh, where is it? Come on. Here we go. How about I say it like this? This is the summary, and then we'll take our break, and we're going to do a bunch of problems. So this is the summary for everything that we just said. If you have a changing capacitance with a closed switch, the voltage stays the same, capacitance goes up, and energy goes up, which is what somebody thought. Now, the issue we just had is if you do this with an open switch, the charge is going to stay the same, capacitance goes up, and energy goes down, so does voltage. And so that's the summary of what we just saw. What we need to do is practice doing the algebra associated with this. We just kind of got the concept down. We're going to take a quick break, come back, and do some problems that discuss this in detail. Before we take that break, are there any questions about that? Let me see if I got anybody here. So it's kind of exciting, and I'm telling you, it gets cooler and cooler, even if it seems boring right now. Check it to see. All right. So I'm going to go ahead and stop the share for a second. By the way, this summary was written on, what problem was this? 25.18, at the bottom of 25.18. That's where that summary is. But yeah, I'll write that up here real quick. I'll check the chat. Tom, usually what you'll do is you'll start from these basics and you'll learn more powerful techniques. So we actually debated this for several years, and we did a study, and we found that students are statistically 10% more likely to pass a circuits class if they have 163 first. And so it's clearly going to help you understand the basics. And I can't help it if engineers do everything incorrectly. They define current a different way. Oh, did I say that out loud? That's supposed to be a joke. But yeah, so they're gonna flip some arrows a different way, and so they're actually going to be a little bit of confusion. But the basics should be a little bit solid, hopefully. Yeah. So, and your lab skills, even though they're not going to be great, they're going to be okay. Right? You'll know a little bit about a DMM, a little bit about an oscilloscope, a little bit about resistors and transients and things like this. So you'll have a base to build from. Good question. Yep. I also teach with a very electrical engineering mindset. I've worked in the electrical engineering department down at UCSB as a grad student and overseas and all over. But yeah, so I kind of have a electrical engineering, and I took my circuits class with an electrical engineer that was big into circuits. So I've got a real EE mindset on this class. So I'm, if you're an EE, you're set up like gold here. All right. So you're going to be fine. And if you're a mechanical and have to take circuits, you're going to be great. All right. I think it's going to be John Garrity. And I know we were talking together. I think he's going to use that Tinkercad program to do some labs there. And yeah, so we'll see what happens. And Dom also teaches it. So yeah. John Garrity went to school here many years ago. And to give you an idea of how smart this guy is, he got tired of writing things on the whiteboard and then having to write them on paper afterwards. So he's like, you know what? I'm going to create my own smart markers that I could take anywhere so that whenever I write on the board, I'll just put 4 dots. And yeah, John. So there you go. That guy's a freak genius, man. Man, so good with anything real, like any real device or circuits. He's the man. So yeah, you're going to get a great education from him. All right. let's take that break. All right. So let's take a short break and we'll come back. All right. Yeah. So, yeah, it's been a rough class, huh? Oh, I found this in the lab the other day. Yeah. Yeah. We'll come back at 5:55, of course, for sure. All right. I'll see you guys in a couple of minutes. All right. What's next? Okay. So hopefully it's a good time to get back into it. I'm going to start with a screen share and kind of maybe look at some. Let's do the simplest possible capacitor in-out problems before we get all crazy, right? So let's take a look at this one. All right. Two capacitors are in parallel. They both have capacitance C when no dielectric is present. All right. So we're going to start doing the algebra behind all of this crap. All right. And the switch is closed and is assume potential difference of the battery is known. Draw the equivalent circuit, equivalent stuff. And so I see. What are we going to do? The idea is we're going to look at this circuit without the dielectric in it, and then with the dielectric in it. All right. And so we're going to try and first, before we get ahead of ourselves, make sure we just understand this simple circuit, understand everything about it. Okay. So that's what I'm going to do. Two capacitors in parallel and they're identical, right? So let's go to the whiteboard. So I'm looking at 25.17a. So notice the very first step in these dielectric in-outs is trying to first understand the basic circuit without the dielectric. So we have a battery here that has potential difference E. We have C1, C2, maybe I'll scoot just a little closer for this one. Hopefully you can read that all right. And then I hope you agree that this is going to go into an equivalent circuit with just one capacitor. Because they're in parallel, we know that, let me give it a little bit more room here. Okay. We know that this one is has capacitance C and this one's capacitance C. When you put them in parallel, it should be 2C because in parallel, the areas add up. So in this case, now let's see, we know the voltage across this one here would be E. And the charge, it's almost 2EC. No, it is 2EC. I don't get tired of that joke. All right. So it's just 2EC. All right. Now, when I bring that back, which thing should I bring back? Should I bring back the charge or the voltage for each of these? This was a parallel. I'm going to bring back the voltage. So that tells me voltage 1, that's E. Voltage 2 is E. And then the charge, that's pretty easy. Whoops, I mislabeled them. So this charge is easy. And that charge is easy. All right, if I wanted the energy, well, in this case, I could get the energy here, 1/2, blah, 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 blah. So the energy here would be, let's see, 1/2 QV. The 1/2 cancels the 2. That's just E squared C. And then I hope, whoops, I don't know, I'm drawing on myself here. And maybe I'll be a little bit lazy this one time. Because these two capacitors are exactly the same, it's probably reasonable to expect that U1 is equal to half of that and U2 is equal to the other half. Or you could plug in this and do it. In this case, I'm just going to say, yeah, well, if they're equal, they're going to split it up. So this is our basic circuit. And now I want to stick in the dielectric and see what in the algebra changes and by what fraction the energy changes, etc. So that was 25.17a. Now we're on to part B. And let me make sure there wasn't anything else before I move on. Figure out everything. Got it. So that's what we did in the original circuit. All right. Hopefully that's not too bad. Let's go take a look at the next part. A physics student decides to make you miserable. Now the physics student is going to open the switch, then insert a dielectric with constant kappa. That's a capital, there's a kappa there. I don't think that's kappa, capital. I think it's lowercase, but whatever. Let's worry about that later. And we're going to stick that into C2. And so notice this is the notation I'm going to use in the book. This is the one that got changed. So in the after state, I'm going to call it the prime state. Okay. So this one is C2 prime. All right. So now the switch, when the switch is open, that battery's out of the circuit. I'm just making some notes here, so I've got the problem.
I've got a quick question.
Yeah, go for it while I'm drawing.
I just realized both of these times where we've stuck the dielectric in the plates have been when the battery has been disconnected. Is there a reason for that?
It's because when the battery is connected, students don't screw it up. When it's disconnected, they do. So I'm trying to do the one that students screw up. Is that cool?
Yeah, yeah.
Yeah, and so, yeah. And so you'll see in the very next problem, take a look. This is one where it is connected. So if you want to do that one, I'm leaving that one for home because students tend to not screw that one up. Is that good? Yep.
Yeah, we're good. We're good.
Yeah, yeah, yeah. All right. So in this case, this is now C2 prime. And so that's the way I'm going to denote that. Let me get this back on the screen. Okay, so now I put this in here. I've got C2 prime. That means the after. So in this case, I'm going to first get the equivalent capacitance again. Before I get all crazy, this should be equal to the switch is still open, but now I'm going to have, whoops, I need a little more space. Instead of C12, something has changed, so I'm going to call it C12 prime. It's a different capacitor. So again, I still haven't worried about anything. Just like every problem we've done, I'm first going to figure out the equivalent capacitance part, then I can do the working backwards part. So in this case, do you agree this should be C1 plus C2 prime? I would add them, but I can't just say it's 2C anymore. In fact, C2 prime, the way you figure it out, that's going to be kappa times C. Basically, the dielectric constant is a multiplicative factor. So if kappa is 2, you're doubling the capacitance when you stick it in. If kappa is 5, you're multiplying it by 5. All right? So this tells you how we deal with these dielectrics. Essentially, all it does is it sticks a letter kappa inside the capacitance equation.
Can I ask a really quick question?
Yeah, do it. Go for it.
So does that mean that obviously kappa is always greater than 1 because capacitance will always increase?
Yeah, except sort of going back to what Nick asked earlier, isn't era dielectric? Yeah, it is, and it's like 1.0079 or something, I think, or maybe it's 0.0007. I forget. Maybe it's 97. So sometimes the dielectric constant is so close to 1, we just round it to 1, which that answers maybe Nick's question more thoroughly. Its dielectric constant is almost 1, so we treat air and vacuum as about the same. Not exactly, but close. Yep, but you're right. It's usually 1 or bigger number. All right. And so in this case, C12 prime, I don't know if you could see that. There's going to be a C plus a kappa C. I'm going to factor that out. Sorry, this is so squeezed in. That would be a 1 plus a kappa times a C there. Sorry, it's just squeezed in there. All right. Well, okay. Now that I have the equivalent capacitance, do the thinking. So in this case, we said, didn't we say switch open during dielectric in or out? In this case, it was being put in there. Okay. So what is held constant? Is it the charge or the voltage when the battery is disconnected? Do you remember?
The charge.
Charge. And so what we say is Q equivalent prime equals Q equivalent from the old circuit. And so what's kind of weird here is the charges may actually move around in here, but I know that the equivalent amount of charge, right? I could have some charge move from this plate to that plate or vice versa, but we're not going to have the charge go out here because there's not a complete circuit. Even though this wire is connected, if the switch is open, right, there's no way for electrons to keep flowing, right? If some of them moved that way, well, there's nowhere to resupply them. They'd be drawn backwards right away. So in this case, by opening one leg of this circuit, it's effectively like you've taken the whole battery out of the circuit. And when you do that, there's nowhere for charge to go. So again, now it's not really like this, but it's effectively like this. This is what we really see in the real world, is we still see a battery there. And we still see this connected, but no current can flow once one leg is opened. All right. In this case, let's do some math now. Well, if I know the two charges are equivalent, maybe I could figure out something. I don't know what we were trying to do. What are we trying to do? Okay, we know that the equivalent blah, blah, blah. Use this information to figure out the charge on, voltage on, stored energy of each one. Okay, well, so in this case, do you agree we now know this charge is still 2 EC? This is the same as before. Why? Because there was nowhere for it to come from or leave to. So that's still 2 EC. And now the rest of the problem is a piece of cake. This is hard, remembering this, right? Well, how do I know it's hard? Because I've seen hundreds of students forget it. So in this case, once you know that, what would be the technique? What would we do next? Don't do it. Just tell me what I should do. I know the charge here, and I want to figure out the charges and voltages here. What might you do next? Any thoughts?
Solve for the voltage.
If I get the voltage, why does that help?
Because since they're parallel, when you go back, the voltage is the same.
Yeah, so here we get the voltage, then I bring that back, and once I have the voltage, then I use QVC again, and I use blah, 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 blah. So the next step would be, so since Trey was crazy enough to speak up, Trey, you want to tell me what I would do here to get the voltage? What equation?
Q prime over C prime.
Exactly, and I like the way you said that. So all we do is we keep this rocking. And so now I've got the primed charge, which happens to be the same as the unprimed, but I do have a new capacitance, which means I will get a different voltage than before. And that's what we saw, right? When the battery was disconnected, we expect the voltage to drop. This gets bigger, so that's going to get smaller than E. And then once you do that, you bring that to here and to here, just like before, and we're off to the races. So far, so good. Let's jump to the solutions and fix this and just finish this, all right? Because we got to get to a couple of these just so you could see it. That was the hard part of this. All right, and so you can see, here's what I did. It's just 2 EC. All right, I just love that. I'm not going to stop saying it. And this gives you all the math on that. And so, hey, this is something I forgot to mention. This is a way to check your work. If you set kappa to 1, that's like no dielectric at all, right? Kind of what Travis was asking about. So kappa we expect to be bigger than 1, but if you set it back to 1, notice we get a 2 here, this cancels that, and you get the same result, E squared C for the energy, or E for the voltage, right? Or 2C, right? This would be 2C if you set kappa to 1. So that's a way you could check your work. You basically set kappa back to 1. That's what this is saying. All right. And then here's another check on your work. We should find that the sum of the capacitor energies equals the total. So remember, we got to be careful. The total energy in the prime case is not going to equal the total energy in the unprimed case. So you can't just say U1 plus U2 equals U prime. We expect U1 prime plus U2 prime equals U total prime. And so if you get used to this habit of that bookkeeping, this stuff is easy. If you don't get into that habit of bookkeeping, this stuff is hard. Let's see what the chat is there. Your dielectric is, well, okay. A conductor has a complex valued dielectric constant. All right. So it's an imaginary number. We're not going there. All right. So we're going to be using insulators for our dielectrics. Okay. Is that good, Alexis? Just assume dielectric is an insulator. All right. Even though every insulator is technically a conductor, it's just a really, 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 really bad one. So yeah, that's good terminology there. All right. Other questions? All right. Whoops. Whatever. This one, 25.18. I'm going to let you do that one at home. It's the slightly easier one. This one is more intuitive to people. Why? In this circuit, when the battery is still connected, capacitance goes up. Voltage stays the same. If capacitance goes up, charge goes up, energy also goes up. People don't seem to have as much trouble with this because it makes intuitive sense. It's very counterintuitive that when capacitance goes up, energy goes down. That's what happens when the battery is disconnected. All right. Oh, these physics students wanting to make me miserable. So I'm going to let you do that one on your own. And then we want to hit this and we're done. Okay. So before I go on to this next piece, that's the dielectric in-out crap. Let me mention there's a couple more problems here. 25 and 26 as well are the harder dielectric in-outs. So if you don't feel good on the dielectric in-outs, I'm going to put this in the chat. So, right, the 25 and 26, we did the two easy ones. There's no way I'm giving you those on the quiz. You know that. I'm going to give you something nasty as hell. So if you want to deal with harder ones, why don't you make sure you can do 25 and 26? And then I was looking, right, on the, let's see. And so I think both of those are on the recommended or required. I think they're both on the required. Well, I think 25 I didn't put on the required, but whatever. If you want extra practice, do both of them. If you don't, just do one of them. And 26, I think, is the one that's required. So if you do 26 and you're still not quite or still not certain, do 25 as well. And then you'll be able to handle the dielectrics if that shows up. The other possibility is this thing that I want to do. So I want to make sure we cover this right now. All right, so that's dielectric in-outs. More on that if we have time in office hours or something. Now, what if we have two capacitors and we charge them? Then you disconnect them from the battery and then you reconnect them to each other. And I've actually showed you this earlier, and let's even see if we can do that. The idea is this, yes. Let me do this really quick. Let's make this one bigger. All right, and so the idea is, all right, let's say we have these two capacitors. I'm going to keep one of these switches. Oh, let's just keep both of them. It'll be faster. So let's say I take this capacitor here, and they've both been charged by a battery, right? And so now what do I want to do? I want to take these puppies and maybe I'm going to disconnect it. And I just want to point out, let me show the values on these. Okay, so one of these capacitors is bigger than the other. All right. And if I could show the charge, does it show the charge on here? I can't remember if it lets me show the charge. Well, I could show you this. I could put this voltmeter out here. And I just want to point out in this case, the voltage across this one is 9 volts. The voltage across this one is also 9 volts. And so now when I do this, if they're both 9 volts and one of them's a bigger capacitor, Q equals VC, let's see, what did this turn out to be? Is this 1.8 coulombs? And this would be 9. Wait, did I do that right? This would be 0.9 coulombs. Q equals VC. V is 9. C is 0.2 or 0.1. Is that a large amount of charge or not? What do you guys think?
1 coulomb's pretty decent, isn't it?
That's a lot of charge.
You're going to die. You're going to die. If you touch these, you're dead. All right. So this is insane. All right. If you want to, you could look up AED, the, geez, I'm forgetting the something defibrillator. I'm
Automated external defibrillator.
Thank you. Right on. And so look up how much energy is stored in those. Calculate how much energy is stored in this capacitor, and they're probably comparable. So yeah, this is probably enough to stop your heart. All right. So yeah, don't lick these in lab. Oh, good thing we're in ERT mode. We don't have to worry about that. All right, whatever. So this is crazy. Let's get back to the question at hand. These are enormous, enormous charges. So now I'm gonna flip this sucker. All right. And so I've got too many lines here. I'm getting confused by all these lines. Okay, so in this case, we have all these charges. Now I'm going to open this switch. That's how you could do this in the real world. I'm going to connect these. And now as soon as I close the switch, think what should happen. And I'll put this voltmeter on here so we can measure it. The voltage going to go up, down. What about the charges? Are they going to move or are they going to stay still? Are these in series? Are these in parallel? Oh, my mind can't take it. This is usually where students lose their minds. Couldn't be the first 4 weeks.
I think the volts will stay the same.
Okay. I don't know who was that Nick or was that somebody else?
Yeah, that was Nick.
Okay. So Nick thinks the voltage is going to stay the same. All right. And then somebody else, what do you think is going to happen to the charge?
I think things will start moving, and that's going to require energy.
Okay. So if the energy changes and the capacitance stays the same, is it possible for the voltage to stay the same?
No.
How do you know? We know an equation. So U is equal to 1/2. Well, wait a minute. Couldn't the charge just change and blah, blah, blah? Well, remember, we could actually, this is where it helps to rewrite this. It's unclear as written right here what's going to happen. But if you rewrite it as U is equal to, remember, C is not changing in this problem. We had a problem where voltage changed. We had a problem where charge changed. Now we're going to have a problem, or sorry, excuse me. We had a problem where the voltage was fixed. We had a different problem where the charge was fixed. Now we're keeping capacitance, which is a property of the plate geometry, fixed, but voltage and charge are going to change. So let's see. This would be Q is equal to VC. So isn't this 1/2 delta V squared C? And so, or we could say U is equal to 1 Q squared over 2C. I don't know. Maybe this isn't clear to you guys. So let's just run it and see what happens, okay? Or any other thoughts before I flip the switch? Any questions or guesses or things you want to guess out?
So would they be like in series technically?
Okay. Ryan thinks they're in series. I'd agree with that. But I think they're in parallel. Do you agree with that?
I think they're both, just depends how you look at it.
Yes, this is the weird circuit that's both series and parallel. Smoke
That's tricky.
that. It'll really get you out there, right? Hello. So this is crazy. In this case, don't these two capacitors have to have the same voltage? Think of one of them, pretend this is the battery. Then this one has to have the same voltage. That's a property of a parallel circuit. But isn't there only one pipe? Yes. So this simplest circuit is actually the most baffling at the beginning because it's both series and parallel. What? I want a refund. Okay, let's get that out of there. All right, so let's flip the switch and shut up. Let's do that. In this case, look at that. Did you see that? Did the charges change? Okay, I hope you saw that. They did change. All right, look at the voltage. We could see that the voltage changed. Do you agree? It's now 3 volts. It was 9. Let me ask you this. Do the capacitors have the same amount of charge on them based on the picture?
No.
No. Do you think they have the same amount of voltage?
Yes.
Let's see. They have to have the same amount of voltage because of conservation of energy. If you had a single electron, let's say we had this electron here and it goes, again, imagine it going all the way around the loop somehow, even though none of them do that. If it was able to do that, it would gain energy or lose energy every time it goes around. And if it gained energy, that would imply, and then you could have a charge go the other way if it was, yeah, anyways. The fact remains, this would lead to an impossible contradiction where the circuit could have an infinite amount of energy for free, and that doesn't work in the real world. All right, so by conservation of energy, this voltage, I'll call this delta V1 prime, has to equal delta V2 prime. So that's one interesting thing. All right, now wait a minute. What about the charges? What do you think is true about this amount of charge and that amount of charge? They're not the same. Do they relate to anything we already knew? This is sneaky. Let me put it to you like this. Some of these electrons came over here and they covered up some of the positives, and then even more of them came over and made this plate negative. So the charges, remember, this plate used to have its positive terminal up and its negative terminal down. So many of these negatives came over this way, and then some of these negatives came over that way. And what happens here is I've got too many drawings. The idea is we've got some minus charges go here and some minus charges go there, but because they didn't have the same amount of charge at the beginning, not all of it cancels. It's not destroyed, it's just no longer excess. Remember, we're not looking at all the charges. This plate is filled with moles and moles of pluses and minuses. What we're seeing here is the excess minuses. So some of the excess minuses go over to the other side, and then they make that top plate neutral, and then even more of them come over and make it negative. And they do that until such point that the two voltages are equal. Crazy, right? All right, so that's the big picture here. So let's get the rules up. Isn't this crazy? I love this stuff. All right, so here's the idea. If they are connected together positive plate to positive plate, that's not what we did, but if you connect them positive to positive, let's follow this through. Number one, a circuit is formed. 2, the voltage change around the entire circuit must be 0. That's energy is conserved. From 2, the potential differences must equal. I mentioned that already. Excess charges, excess charges, not all of the protons and the electrons, just the excess ones, effectively flow freely. And again, really it's the electrons moving. And because the electrons move from one region to another, you can leave a positive charge or get rid of an excess positive charge. And that's going to split. All right. And then because the excess charge is not created or destroyed, the two caps must split it up. So the initial excess charge should equal the final excess charge when connected positive plate to positive plate. The exact opposite is true if you have positive plate to negative plate. There you get the charge difference will equal the net excess charge on the two plates. So the idea is if you connect them plus to plus, their two charges add up and split up some way, because there's no way for electrons to cancel some of the pluses. If you connect them plus minus, like I just did, well, you're going to have this scenario where some of the charges cancel out, but they don't disappear. They're just neutral and they're no longer excess. And then whatever's left over gets split between the two. That's a lot of information. Did that make any sense at all? Let's see what you guys are thinking here. That's crazy. This is page 94 here.
Can you show us on this? Oh,
go ahead.
Go for it, Nick.
Yeah.
I need the screen share again so I can see it.
My bad. Sorry.
That's okay. We took a while to say anything.
Yeah, no. It's just Zoom. Zoom sucks.
So down there at the bottom where it says Q1 minus Q2.
Yep.
Yeah. Would it work the same way if you say Q2 minus Q1? Does it
Yeah. And so you're absolutely right. It doesn't matter. I guess you could even do this. How about I say it like this? Absolute value of it. And then the idea is, I don't know if you remember, but when we talked about capacitors originally, and I mentioned there's this equation, Q equals VC. And I'm trying to do the delta because technically that's what you should do, but nobody does that. Anyways, this was the charge on one plate that was positive, but it was also the charge that was on the other plate and negative. So you could say this is the magnitude of charge is equal to the magnitude of voltage times the capacitance. And then you could say that would be, and so does that address your question, Nick?
Yeah.
Yep.
Perfect.
You could do it either way. And if you just slap an absolute value, yep. Cool. Okay. So Ryan, did that address yours?
No, I was just gonna say, could you maybe show in the simulator just really quick what you mean by like when you connect positive to positive, this is true.
Yeah, let's do it. Let's do it. How
Positive
about
to negative, this is true.
Yeah. Here. All right, give me a sec here. All right, I'm gonna open this up. I'm gonna clear my screen. And so that was the last thing that we needed to cover in case you're worried. All right, so I'm going to open this up to, I guess I only need one. So look at this. I'm going to set this one here. Let's pick some easier numbers. How about 10? Okay, and I'm going to discharge both of these. And let's just do this here. So I'm going to plug this onto this one and plug this onto, oh geez, come on. There it goes. That little fire was the tremendous amount of current. Okay, so that one's charged. Notice it's open up here. See where I'm wiggling? An open switch is like infinite ohms. It's infinite resistance. A closed switch is like 0 ohms. So now that allows me to come over here and let's I could connect this one. There's no closed path yet. So I'm going to pick the different size battery. Let's say 50, whatever. Let's pick an even number because that one's 20, right? Let's say 40 volts. All right. And so now I'm going to connect this side here. And when I let go, we get that massive current. That's what the fire is supposed to represent. I'll get the battery. So now they're all disconnected. Is this helping, Ryan, or not? Take off anytime you need to, anybody. I'll just finish this out. Yeah. So now let's do a quick check. You got your calculator handy? Okay. So you can see I flipped a polarity here. Again, -40. If I switch the polarity on the leads on the DMM, I'm still going to get 40. I don't care about that. So how many, I got to figure this out. Q equals VC. So 40 on clear. So 40 times 0.2, right? So that's 8 coulombs. Jeez. All right, so right now this one has 8 coulombs. All right.
Okay.
And then the other one should have, let's see what that one was. This one, the voltage across this one. Now remember here, it's okay because this switch is open that they have different voltages, right? Because this switch is open, some of the voltage is taken up across this open switch that has infinite resistance. So it's okay that these two capacitors don't have the same voltage right now. They will after they come to equilibrium once the switch is closed. So this other one just has 1 coulomb, right?
Oh yeah, yeah.
So tell me, initially, do you agree that Q1 plus Q2 is 9?
Yeah.
So, and now they're connected plus to plus. Agreed?
Yeah.
The positive plate
What
of
do you
this
mean?
one, this one's positive plate is connected to this one's positive plate.
Oh yeah, yeah.
Right? And so now when I close the switch, will there be any cancellation or not? Will there be any way for the minus charges to cancel some of the excess plus charges?
Yeah.
No. So
No.
here's the idea. See these electrons? There's an air gap between this plate and that plate. There's an air gap between this plate and that plate. If we assume that is an insulator, there's no way for these electrons to get over to that plate or to get over to that
I got
plate.
you. Oh,
Does
I
that
got you.
make
Okay,
sense?
yeah.
And so
Yeah.
in that sense, there's no way to get any of this excess charge canceled out. So let me undo somewhere. Okay. So now when I close the switch, is there any way for excess charge to cancel out?
No.
No. So in that case, let's close the switch. How many total coulombs should I have after the fact?
The same.
The same. So now look at this voltage. This one's at 30. What should the other one's voltage be at? The switch is closed now. What has to be the voltage around the entire loop? The change around the entire loop must be
0.
0.
The change in volt. Yeah.
So then what has to be true about this one's voltage? The same.
It should be the same. Yeah.
Yeah. And so the idea, here's the trick. If we always use black and just follow these counterclockwise, this one I go up 30, right? And then I'll just keep following it around. Just keep following it around. And I'll keep following it around. This one would be negative 30. So the idea is you add 30 on the left, then you subtract 30 on the right. More on that later. But so
okay.
is that cool?
Yeah.
If I am very careful with the polarity going all the way around, I have 30 volts up on the left, 30 volts down, because I'm exiting on the plus terminal on the way up on the left. I'm exiting on the minus terminal on the left on the way down, on the right on the way down. Right, whatever. But I just want to point out this one's going to have 6 coulombs because it was 30. This one's going to have 3 coulombs because it was 30. And notice Q1 prime plus Q2 prime has to equal 9 again. Got it?
Yeah. Okay. Yeah.
And then in the previous case, if we flip them around the other way, right, then some could cancel out and you might get a number less than 9. You should get a number less than 9.
Yeah. Okay.
helping?
I see that. Yeah. Yeah.
All right. And I know we're a little bit over. We're 3 minutes over, but I just want to point out the rest of these problems. If we look, I think I kind of, whoops, I should go to here. So you can see I kind of did what we just did. I do it with E's and C's so you can get a feeling for that. I do it plus to minus. And then this is probably a good one. So I'll be straight with you right here. I prefer algebraic questions, but as Ryan just noted, it's almost impossible to get these unless you do a few with numbers first. So I highly recommend, you see I did a couple of these with numbers for you that you can do at home, and you could follow along with the solutions for 21 and 22, right? And then after that, this is kind of where oh wait, this one has numbers too. Oh, I see. So there's a bunch of them with numbers there for you to practice this. And then, oh, I guess I did them. Oh, there's the dielectrics. These ones help you with concepts. And so the 27, and I don't think those are required. Let me just check. I forget which ones are required.
Yeah, you have 27 as required.
What are we? Chapter 20. Oh, okay. So I think I said 28 through 30 is required, right? So, or, oh no, 20, you're right. 26 and 27, right? So yeah. And I think, did I ask you to do 31 as well? But so these extra ones down here, if you're still having trouble and want to do it with E's and C's, you can see it there. Okay. Yeah, there's some variations here, and they're all basically the same. So at some point you got to just be like, come on, I know this or I don't. But if you need the practice, it's there. If you don't, there. All right. I can't believe we made it. This is like crazy. Stop the live stream.